Good morning, everybody. It's a real pleasure to be here. It's the first time for me attending the conference and being surrounded by so many experts. It's a little bit overwhelming, so I'll do my best. From the speaker before, my talk, of course, is tackling the similar topic, but I'm a medical physicist, so it's going to be a little bit of more of a technical perspective. And in some point in my talk, I'm going to be revising the very basics. I remember from my mentor explaining to me once on the day, Cynthia McCullough from Mayo Clinic, that what you really need to understand is the basics. So usually everything goes back to the roots, like a tree when a tree is growing. As I say, I'm a scientist from Siemens, and although most of the examples I think are going to be applicable regardless of the manufacturer that you're using at your institution, the examples I provide will be mostly from Siemens systems. So I know this might look like a marketing slide here, but what I wanted to point out with this is that for most manufacturers, in the example here is Siemens, irrespective of the CT scanners that we sell today, most of them are now able to do lung cancer screening. Not all of them can do cardiac CT, coronary calcium CT, most of them. In our fleet, the only one that cannot do, for example, lung cancer screening is a dedicated head scanner that we have. But we have this all the way from our entry-level systems all the way to our latest system, the photon counting scanner, the Neotom Alpha. There are also a very growing trend in being able to bring this technology to a mobile solution. So some of these, and these systems are not only capable of doing lung cancer screening, that's definitely a number one motivation, but the systems are also capable of doing coronary artery calcium. And you know, all manufacturers will have different opportunities to provide you with solutions for, in the scanners I mentioned, different technologies to help you reduce the dose and maybe to make the workflow a little easier for your technologies, and you know, automating some of the results that you get routinely in the practices. I wanted also to ask that question to myself as I was preparing this talk, and is to look at where are we right now in 2024? Are we really starting from scratch? And of course, the answer is no. I mean, this conference is a great example that there is a lot there. Being a physicist, I normally start with the AAPM. I'm based here in the United States. And I think a very good starting point that is probably used by a lot of your practices if you are in the United States are the lung cancer screening protocols provided by the American Association of Physicists in Medicine. You know, they have different details. They also give some ideas related to the appropriate CT dose index values. And importantly, they provide sample protocols across most of the existing manufacturers. So you will find examples not only from Siemens, but again, all major vendors and other that you probably will have. And many of these, of course, also outside of the United States. Again, for many of them, you'll find very specific description of how to do the acquisition and different recommendations. There is, however, one important miss, I guess, on some of these protocols, is that not every feature, especially on the reconstruction, might necessarily be target for quantification. And I think there's a few of those protocols that maybe miss the mark on that, I must acknowledge. And some of that, for instance, I would like to give a shout out more to the small nodule biomarker committee. Some of the members actually of the committee are here in the audience today. And as you will see here, there is a very detailed orientation in how to pursue these protocols and how to, again, take them from being good protocols to use in everyday clinic, but actually to do proper quantitation. Again, taking a very detailed look to how they're going to be used clinically, error bars, so forth, so on. And I don't know if everybody's familiar in here, but Kiva no longer exists. So now there is a new group called the Quick. But I know the shout out to the group, the small nodal group that is still actively working on the topic. I also found, and I wanted to highlight one of 4 papers actually that I found, and you saw some of those from the prior presentation. This one actually was from Dr. Jankelevich. That actually, this was a collaboration between the Society of Thoracic Radiology and the Society of Computed Tomography here in the US, where back in 2027, they kind of described the status of what about doing coronary artery calcium in non-contrast, non-cardiac chest CT, definitely highlighting the opportunities that are there. And this very nice example, actually, from a paper, both from Dr. Jankelevich and Dr. Heiker here. Now let's go to the basics that I kind of promised early on. So I want to put a side by side a little bit on how we do this acquisition, just to see what's different, what's in common. It's very common that these examinations are done with tube potentials around 120 kb. That's pretty universal. But of course, there are variations because there are interests to push the limits of what can be done in terms of radiation dose. So sometimes for lung cancer screening, you can use selective photon shields, like, for example, thin filtration. On coronary artery calcium, there is also a lot of impetus to try to do different KBPs, for example. At least for calcium, when you want to quantify, you need to realize that when you change the tube potential, the Hounsfield unit actually is going to be changing as a function of the KBP for calcium. So as you're doing the acquisition, you'll have to consider this and make sure that your manufacturer, the reconstruction on some of the steps along the workflow, this is considered and corrected for. In both type of examinations, there are MA modulation, and in the case of coronary artery calcium is gated. The actual radiation exposure tend to be a little higher in calcium screening scans. It doesn't need to be, but that's just more average. And in the case of the coronary artery calcium, in an ideal scenario, you want to do those with gating. In terms of collimation, again, very compatible, although for cardiac CT, usually the threshold tend to start more at 64 detector rows. Temporal resolution, of course, is important for both. They are definitely more strict for coronary artery calcium, and they tend to navigate, you use this idea of the partial scan, so the temporal resolution tend to be much higher than for lung cancer screening. That's not to say a lung cancer screening wouldn't benefit from having higher temporal resolution. In terms of reconstruction, light thickness is also a consideration. For lung cancer screening, we have systems that can provide you 0.2 millimeters slide thickness, all the way to 1.5 tends to be the recommendation. Coronary artery calcium, pretty universal, 2.5 to 3. Kernels, very compatible. And iterative reconstruction of deep learning methods, I think for lung cancer screening, I think there is relatively good consensus they're appropriate to use. For calcium scoring, although they can be used to help, it's a little unclear whether this could lead to some under or overestimation. So it's something that probably will have to be done with care, at least based on some of the existing literature. To gate or not to gate, again, I go back to that paper I mentioned earlier. There was a lot of the key advantage, disadvantage outlined in that paper, I think are valid today, and maybe we can discuss that later. Obviously, if you want to be truly quantitative, also for coronary artery calcium, I think gated is needed, and this is where the best evidence is. In the near future, this is an example from Siemens. In our latest scanner, we actually are able to do both calcium scoring and lung cancer screening at the same time in a single scan that is gated. This is an example where you actually, with a CTDI only 1.3 milligrade of this particular example, there is a lot of improvements in the deep learning. This graph here is specific to Siemens, showing how we can really automate and have excellent correlation for the results for coronary artery calcium. There is a lot more that can be done with this scan, and I guess I'll leave some of those to the discussion. Finally, there is also many more opportunities for concurrent evaluation of coronary artery calcium, like, for example, in SPECT or PET examinations. With that, I want to thank you for your attention.